for the final talk of the Hiroshi test here at Call the IPMU. We're having to have Eric tell us about features and fantasies of moduli dependence in CFT.
We need to put the microphone.
Oh, I see. Very nice. Oh, that's very good.
It's loose. Yeah, the direct connection is sometimes loose. It's coming. Yeah,
Okay.
it's a little bit unstable. Yes.
Yes. Okay.
Great. So, thanks for the introduction, and it's a pleasure and honor to be here celebrating your 60th birthday, Hiroshi. It's been a pretty lovely couple of days from a physics point of view, but also from the point of view of getting to know your other half. This is a bit like being the dark side of the moon. As someone who was at Caltech for all of our interactions, turns out it's a lot like the bright side of the moon. So it's good. Yeah, it's been an interesting experience to hear everyone's reminiscences and experiences with Hiroshi, who's done so much in his career, physics-wise and non-physics-wise. And so let's see, is this working? So, okay.
I see the mouse.
So, today has been so great that actually I'm happy to announce that subject from final approval from the authorities, Hiroshi will actually be a weekly event from now on. This will alternate between Caltech and IPMU for the foreseeable future. There'll be an annual meeting of the Aspen Center for Physics. There will be require status for full attendance, and if you want some more information, you can go here.
So I'll be forever 60.
Nice. That's right. Great. So one of the reasons this has been a special visit for me is not related to the workshop. So I grew up in Tokyo from age 2 to 8, and this is my first time back. There's also a picture of me in Shibuya, where I lived. And I was 5 or 6 or so. So this took place in 1989, let's say November 1989. And if I remember this day correctly, we were headed to the local library to get the latest issue of Nuclear Physics B. This paper appeared for us to take about something, the string expansion. And I think that's what my mom was carrying in this bag here. Read it. And so this is my first experience with Hiroshi. But the real first experiences came at Caltech, where I was a postdoc from 2017 to 20. And it was a lovely place to be a postdoc. Hiroshi gave me, all of us the freedom to pursue what we wanted to pursue, an enriching environment. We organized the Southern California String Seminar, which is always a nice event, with some familiar members of the audience who were in attendance here from just down the road at UCLA. Hiroshi is behind the lens, as is often the case. But actually, my first experience with interacting with Hiroshi at Caltech came in 2012. So I was a student at UCLA, and I gave a talk in the spring of 2012, I think, at Caltech. And it was a really great talk. I learned from Hiroshi's questioning in part that I needed to be better prepared when I gave seminars. I was a grad student, perhaps this could be excused, but at the very least, it was a great learning experience. And in the process of Hiroshi questioning me about what exactly had been established, what was conjectured, what was believed, and so on, this was the beginning of my learning what you might call the Hiroshi rules. Talking to Hiroshi. So first, be precise. Second, be efficient. And finally, be prepared. I think this is good advice for anyone who wants to maximize the experience of talking physics with Hiroshi, and I myself try to keep this in mind in general when I interact with physicists across the board. So, of course, Hiroshi has worked on a huge number of topics with a huge range of techniques, and often there's a strong mathematical bent to them. And I'd say if there's a sense in which most of us are localized somewhere on a spectrum between physical physicists and mathematical physicists. Hiroshi is everywhere on that spectrum. And actually, in doing some research for this talk, I learned something which Hiroshi might not have discovered, which is that actually his H index is the sum of the three smallest. This was true as of last night. It might have changed this morning. But this seems to be a time-dependent Newstein phenomenon that Hiroshi did not discover. Hiroshi's papers I find to be an admirable balance between the big picture. There's always a creative insight about something topical and important, but there's a calculation and it is done and it's done right. It's something to strive to. And as we all question what is string theory, I think a lot of Hiroshi's work has attacked this question from so many directions that he's really had to broaden whatever the answer is to that question. Here's work from Hiroshi's abstracts. You may be familiar with these. The bigger words are stated more commonly. It's a bit of a silly thing, but it tells us something. You see many familiar words. I notice anti-D here, which makes sense because Hiroshi, with his boundless energy, is not much of a sitter. Another thing you might notice about this, which is amusing, is that the word conjecture is quite big, actually, compared to some of the words. Hiroshi is an excellent conjecturer, I would say. The conjecture is in particular give us all to think about something which seems plausible enough to be true, but has that distance from being provable that keeps it tantalizing. Finally, this has been emphasized in a few talks already, really most of them. Hiroshi has done so much for our field, not just for what's in the papers, but for what he has facilitated for the rest of us. And I think that when we look back on Hiroshi's legacy, it's not necessarily clear which will be that which had most impact, the papers themselves or all that he's done to grow the science for the field. So I personally want to thank you for that. I benefited from that as a postdoc at Caltech, and I think we all continue to through your hard work. So this book is a collection of some of my work, published and unpublished, which is inspired by Hiroshi's interests and curated to that. There will be a few parts. First, we'll focus on aspects of moduli-dependent CFTs near weak coupling. I'll transition to sort coupling, and then there will be some final fantasies, various thoughts and fantasies sprinkled throughout to keep it interesting and to try to stimulate further feedback about what kinds of dream scenarios might actually be true in this world of string theory that we're trying to understand more deeply. So, this topic will take place in two dimensions. I'll make some observations about rational points in moduli space. Okay, well, that's an easy one. Still fun to see, but good. So, obviously, Hiroshi's written many papers on 2D CFT from different points of view. Some of them are about structural properties of 2D CFTs that follow from symmetry, but not always in obvious ways. So there's a kind of argument that he sometimes employs, which I want to shine a light on and employ myself, which is to try to impose and extract the consequences of number theoretic properties of the 2D CFT data. So there are several papers, some of which I mentioned here. Say, for example, studying the twist gap in CFTs with U1 affine symmetries or rational CFTs. They use this kind of argument where it's really rationality that's being used, but the consequences of rationality had not yet been discovered until Hiroshi and collaborators thought deeply about it. Of course, the constraints of rationality in CFT have a long history. And this is a quote from Moore Seiberg's naturality paper, actually. Let me highlight the last sentence, which is, only when one has taken into account all available symmetries does physics become rational. But there's kind of a converse of that, which I think is worth lingering on, which is that, let's put it this way, only when one has taken into account the rationality of the physics do the symmetries become understood. So I'll try to explain a bit what I mean by that. But in the big picture, I think these kinds of results indicate a general shortcoming in the way we do modular and conformal bootstrap in 2 dimensions. So we know many of the constraints that 2D CFTs have to obey. Here I've listed, let's say, 4 of the main ones. The first is modularity, the modular invariance of the torus partition function. The second is positivity, aka unitarity. The third is that, at least for a compact CFT, which is often what we're interested in, the spectrum is discrete. And finally, not only that, but the degeneracies are integers. And that last one, of course, is tricky. And we know that recovering integers gravitationally is a challenge, but even understanding the consequences of imposing integrality on CFT bootstrap problems is an open question. So how would we grade this so far? Well, modularity and positivity are the cornerstones of the modular bootstrap in 2 dimensions. So let's give them a green light. We understand how to work with those reasonably well. Discreteness, less so, and integrality, very little. And that's clearly the most refined condition. So this sort of makes sense. But there are some constraints that we know are there. We just need to understand how to harness them better. So what is the space of 2D CFTs? That is the big question that all these efforts are trying to get at. And we imagine that, at least for Virasoro or Super Virasoro CFTs without extended algebras, our CFTs form a small corner of this landscape. I mean, one abstract construction of irrational CFTs is to start with a rational point on a conformal manifold and deform away. And exactly marginal operators of dimension 2 are those which, when added to the action, deform us away from the rational point. And I think it's very well motivated to study this kind of setup to understand better the space of irrational CFTs, because we know, at least in principle, how to define it. Whereas we talk about an isolated irrational CFT, this is much harder to conceive of what it could possibly look like. And Hiroshi has done some nice work in the past couple of years in this sort of. Of course, many works years prior as well. But these have inspired some of what I'm about to say. And so I'll talk about a result from a paper from 2020 with Justin, in the audience, which is a rigorous bootstrap bound on rational points in modular space. And it's very clean bound. So the result is the following. If you assume that the 1-point function, the exactly marginal operator in the torus is non-zero, then there must exist a non-polymorphic operator phi with non-zero OPE coefficient with the marginal operator O, with dimension bounded above by this number here. C is the central charge. This is an exact result in C. And this DO is the rank of the one-loop dilatation matrix. That is to say, the number of operators that acquire first-order anomalous dimensions in conformal perturbation theory. I'll explain this later. So this comes from, but let me also just note for now, if O happens to be diagonal, then this term disappears and the bound is even stronger. So this is the case that includes all of the possible cases. Okay. So if you're familiar with the bootstrap, this is a clean bound that is kind of the form which we seek in irrational CFTs. And so I'm going to explain where this comes from and suggest some strategies to achieve this outside of the rational setting. So where does it come from? It follows from imposing modularity, discreteness, and integrality, but without using positivity. And so for that reason, it's also intriguing in this broader context that I discussed. What's the proof? We'll actually walk through it. It's simple enough and I think as elegant and uses a nice result from math. The logic is, I think, clear. So let's state it here before going into a little more detail. The idea is to consider a 1-point function on the torus of the exactly marginal operator O. This is modular covariant, but it's non-positive in the Q expansion because it's linear in the OPE coefficients. But rationality implies that this object is a gluing on the left and right of 2 vector-valued modular functions, modular forms. Now, when O is exactly marginal, as it is in the case of interest, it turns out that the components of these vector-valued modular forms have an integer Q expansion. And there's a result known as the unbounded denominator conjecture, which tells us that there are some strong consequences of integrality, which happen to hold in this case because of point 3. Putting these things together, you actually get this bound here. Okay. Okay, so let me explain this in a bit more detail. So in rational CFTs, there's a finite number of modules with respect to the extended chiral algebra A. I don't need to specify what A is for this to work. Okay. And so this one-point function O is excluding by excluding matrix N these left and right VVMFs. Let's parameterize these components as scaling like q to the n naught I, where I labels the component of this DO dimensional vector valued modular form. Okay, so there are T sub O components. And they follow a conjecture, which is actually now a theorem as of about a year ago, but was a conjecture at the time of our paper, going back some years, is the unbounded denominator conjecture, which is a statement that if these are rational numbers, and if they have an integer or rational Fourier expansion with bounded denominators, then all of the components are actually modular functions for gamma n, which is this subgroup of SL2Z. I guess we can prove the desired result about these exponents and then put things together. Okay. So what is the desired result about the exponents? The result is the following. If there's one component which is modular for gamma n, then the minimum of all of the exponents of this VVMF must be negative. In other words, there's at least one component which in the q goes to 0 limit diverges. Okay. So the proof is nice. It's a sort of physics proof. Let me show you a picture that proves it for the case of n equals 2. Here's the fundamental domain for gamma 2. Now, we start off by assuming that some component vi vanishes at the cusp, so it has an n naught I, which is positive. We want to prove there's another component where this exponent is negative. Okay. So this component has a 0 up here at infinity. Now, modular functions of gamma n obey what's called a valence equation, which is the sum of the orders of poles and zeros everywhere in the fundamental domain. And the statement is that that sum must actually vanish for a modular function of gamma n. So there's a 0 here. So that means this component has a pole down here somewhere. But let's form the SL2Z invariant combination, v squared. And note that with an SL2Z transformation, we can move these points back up to infinity. But because this is SL2Z invariant, that means there's another component which has a pole up here, which is what we're trying to show. Okay. So now we can return to the one-point function, which has an expansion in torus one-point blocks. In this case, these are the components of the VVMF. These blocks FH are labeled by the left and right chiral dimensions. And we take them to scale like this as q goes to 0. Okay. Yeah, question?
Question. Is the group still goes something like K over plus? Is it something else? Or
yes, in this case, it's an invariant function, so the right-hand side is 0. Yep. Yep. Great. Great. So something special happens when the external operator has chiral dimension 1. The special thing is that these one-point blocks, which are in general very complicated, much like the sphere 4-point blocks, actually just become characters of the relevant module of the chiral algebra. And so in particular, their expansion coefficients are integers. Why does this happen? Well, a nice thing about an exactly marginal scalar is that on the left and right, it just has h and h bar equal 1. So chirally speaking, you can think of it as a current. And so if you think of a current, then all of the operators in the module have the same charge. And so you're just counting states, and that's how these blocks become characters. Okay. So we have integrality in the setup. We apply the previous results. You take care to glue left and right consistently with the valence formula for SL2Z. That's where this extra term comes from. And here's the result. Because we're computing one-point function, the source contribution of this light operator phi must couple to O. And so this is equivalent to saying that this operator requires a first-order anomalous dimension, which explains the terminology earlier for DO, the dimension of this VVMF. So in the context of the bootstrap this year, where 12 is evocative, it is the sought-after threshold for VSOR primary dimensions in irrational CFT. Sought after because modular bootstrap has yet to achieve this in large central charge. We're in irrational CFT, so we haven't derived that result. But we can take large C if we want to, as long as we take care to scale the dimension of the chiral algebra appropriately, because the central charge is always at least, in irrational CFT, the central charge equals the central charge of the currents. So as C goes large, central charge of the current sector, and therefore the number of currents must go off to infinity. And gravitationally, you can think of this as the threshold for black holes in a pure gravity theory for this higher algebra with lots of higher spin fields. Our number of currents is going up to infinity. Okay, so you have some algebra G in the bulk for some Chern-Simons theory on the left and right. The boundary Carroll algebra would be the Drinfeld-Sokolov reduction of this, and that's what I was calling A. And so here, this has a gravitational flavor to it if you think of the gravitational theory as this higher spin theory with lots of currents. But this operator phi, I'd like to emphasize, is not holomorphic. So the operator which obeys this bound is necessarily a matter field. It is not just one of these currents, because we're looking at a torus one-point function, and we're using the Carroll algebra blocks. And the identity does not appear in this one-point function. So this really is a primary operator, which is non-holomorphic. And for that reason, it has the flavor that you'd like in this context. Now, the big question is, can we extend this bound away from the rational point on the conformal manifold? Well, I don't know if you can do this a finite distance away. Certainly in the neighborhood of the point, the dimensions vary smoothly and infinitesimally. So there will be some operator which lies at or below this bound, plus small corrections. But whether we can answer this question more satisfactorily might be helpful for thinking about the generic bootstrap problem. Okay. Now, there's a second result implied by the same construction, which is that all the OPE coefficients for operators above this bound are actually determined by those below. Why is that? Well, take a difference of one-point functions, and then if this difference doesn't have a power of q, which is negative, then this thing vanishes because of the result we proved earlier. So the light OPE data fixes the heavy OPE data. This is the kind of feature I call determinacy, and there's an analogous result for the spectrum. Let's define the twist, which is twice the minimum of h and h bar for a given operator. As we probably all know, in holomorphic CFT, the spectrum of twists greater than C/12 is determined by its complement. So holomorphic, or rather meromorphic modular forms with weight 0 for SL2Z have this property, right? The non-polar terms fixed by the polar terms. The surprise, at least to me, is that in relational CFTs, this is still true. It follows now from this property of vector value modular forms I proved earlier, applied to a difference of two putative partition functions with the same light spectrum. That difference must vanish. So this raises the question whether a twist determinacy or perhaps dimension determinacy could hold in all 2D CFTs in one form or another. In this paper from about a year ago, we addressed this question using very different techniques. There's a preliminary answer to it, but I won't go into that here. So the line move up in dimension, and I'll talk about a CFT distance conjecture, which Cumrun, Leonardo Rastelli, and Irene Valenzuela and I formulated, which, as the name indicates, obviously was inspired by Cumrun and Hiroshi's own distance conjecture in the context of quantum gravity and so on. So, of course, field theory suggests basic principles for field theory. This is one of the reasons we love it. And one apparent feature of string theory is coded in the Swampline distance conjecture, which, just to remind us, if we need it, can be phrased in this way: infinite distance limits in moduli space, necessarily accompanied by a tower of light fields whose mass is vanishing exponentially in the geodesic distance from the interior. This includes a specific form of this general point of view that there's universality in moduli space in quantum gravity, articulated in Cumrun's solo paper that preceded this one, and just more generally throughout this paper. So the goal is to formulate a precise analog of this in conformal field theories. And before doing so, I find it amusing that in the acknowledgements for this paper, I noticed that Hiroshi presented these results preliminarily at his 60th birthday for Michael Green. So that's a nice touch. I wish I had something so impactful to present here, but alas, let's see. Some of my fantasies might eventually grow into something more. So let's get some intuition for what the analog might be. And I think with enough experience, this is perhaps somewhat obvious, but still quite non-trivial. So here are some features of the swampland distance conjecture. And here are some CFT analogs that are rather direct. Okay. So if we're talking about varying scalar moduli, well, in CFT, the context in which we literally have moduli are when we have exactly marginal lengths. The moduli space becomes the control manifold. The metric in this moduli space, the one here, the natural one is the Zamolodchikov metric, which is just the matrix of two definitions of these exactly marginal operators. This is critical that gravity is coupled to the rest of the theory, whatever it is. And here we want to consider local CFTs, that is, those which contain a local stress tensor operator. Masslessness in gravity should correspond in some way to a saturation of unitarity bound, which, if you think about ADS, is exactly what you'd want. And exponential with your resistance, well, that should maybe just be an exponential decay resistance, but that deserves a deeper explanation, which we'd like to find. Okay. Now, in these symbols, free CFTs are at infinite distance. Okay, so if you think about taking a CFT with a gauge field, take the gauge coupling to 0, this theory goes to infinite distance in moduli space. And abstractly, we can characterize what a free CFT is, say from the bootstrap point of view, as a higher spin CFT, or what you'd like to call a higher spin point on the conformal manifold. This follows from the results of Maldacen and Sheboyega, which was that if you have one current which has spin greater than 2, which is exactly conserved, there must be an infinite tower, and moreover, the correlators are those of free theory. So in that sense, higher spin symmetry and free CFT are interchangeable. Here we've just written the unitarity bound for spin J and the relation to mass in ADS to motivate this bullet point here. So let's make some conjectures. The first is that the arrow actually runs in reverse. All CFTs at infinite distance, higher spin points. This does not follow from anything I said, but it's certainly consistent with what we know. So an equivalent phrasing of this in terms of the global property of the conformal manifold is to define the diameter. So if I parameterize the couplings as T, Ti, then different points are labeled by couplings T. And so if we define the diameter in this way, in an anomalous dimension for a spin J operator, in this way, in particular, we define this as the minimum anomalous dimension in a given spin J sector of the Hilbert space at point T. Then the statement is if the infimum is positive for this anomalous dimension, that is, if it is not 0 anywhere, including at the boundaries, then the diameter is finite. The second part of the conjecture generalizes the second part of the conjecture in the swampland context, which is that these infinite distance points, this approach to unitarity happens exponentially in the geodesic distance with respect to the Zamolodchikov metric. Okay. So first point is the statement, remember, that it is a higher spin CFT, which means you have an infinite tower of higher spin currents, at least one such tower. So the statement is the restlessness, the consumption becomes exact exponentially in this distance. And the equivalent to saying that the Zamolodchikov metric near the cusp becomes hyperbolic as you go toward infinity. So the metric approaches this as you go toward any given cusp. Here I've just picked sort of a one-dimensional case to demonstrate this, where you take m tau to infinity. Here I don't want to think of this necessarily as a classified gauge coupling, but that's useful to guide the mind. And of course, in all cases we know that's what it is. And so this is consistent with known cases, say in 4-dimensional superconformal theories, but the statement is that this exponential property follow from this.
Why gamma 4?
Yeah, good. So a higher spin algebra need not include a spin 3 current, but it must always include a spin 4 current. You can have even spin in higher spin algebras. So that's why I get it.
You are excluding D equal 2, so there are counterexamples to this.
Yes, I'll address that. So I try to do it. Hyperbolicity is equivalent to this because anomalous dimensions for higher spin currents always turn on at first order in perturbation theory away from a fixed point. Right. This follows from Maldacen and Boedov. But for somewhere the CFT data gets corrected, therefore the CFT is no longer free. Therefore, there can be no conserved higher spin currents left. So they all acquire an anomalous dimension of this order, and that means they all have an exponential approach. There's a refinement of this statement, which is that there's a convexity or monotonicity of these diameters. If you look at spin J submanifolds of the conformal manifold, this is a more refined point. The leading trajectory of operators in any CFT is known to be convex and monotonic. And so that just carries forward to this statement when you look at spin J submanifolds of the full conformal. Okay. So some comments. This is meant to hold an arbitrary central charge, in particular a finite central charge. One can take large C limits as desired. If you do so, well, we're not close to the Einstein regime, talking about theories with higher spin currents. So there's no a priori relation to other familiar swampland conditions like the weak gravity conjecture, the FT bounds, and so on. It would be interesting if there were a tighter connection, but we don't know of a rigorous one. Is there another question? Yeah. Previous slide, you said? Sure.
Is the J same as the 4? Or I'm confused.
No. So the claim that this condition is just the statement that there's an infinite distance point. And so if there is, then the diameter diverges logarithmically. But if you look at the diameter of the spin J submanifolds, those diverge logarithmically, but in this ordered set. That's the statement. Yeah. This J is the same as that J, yes. Spin J operator on the leading trajectory. Yeah. Okay. So why not two dimensions? Well, the short answer is that all 2D CFTs are higher spin CFTs. From the point of view of the global conformal group, composites of the holomorphic or anti-holomorphic stress tensor have arbitrarily large even spin. What's also the arbitrary way to get around this, and I think nor should there be, it's another conjecture made long before ours, that in two dimensions, the scalar gap actually closes at infinite distance. So the only way to go to infinite distance is if the scalar gap closes, as in a decompactification limit. This is weirder, because now a ground state becomes non-unique and so on. You have a continuum tightly. But I'm really to prove this using algebra invariance in two dimensions. I don't know a way to do that yet, but it's something to think about. And I'd say also the existence of rational CFTs in two dimensions, of course, makes the landscape of 2D CFTs different. It's not clear whether there's anything interesting to say about rational CFTs in this kind of context. For example, there's no clear relation to the Zamolodchikov distance between rational points and other points being especially interesting quantity, but this might be useful to think about as well. But to summarize what we seem to believe and what we've conjectured, all the conjectures in D greater than or equal to 2 dimensions can be phrased uniformly as follows. At infinite distance, the twist gap vanishes. By that I mean closer to 0 above the unitary. So if we're moving away from this, let me make a few more speculative remarks. A plausible conjecture, which is suggested but certainly not implied by the hyperbolicity of the Zamolodchikov metric near the cusps, is that in any dimension, the Zamolodchikov volume of the conformal manifolds is finite. This was conjectured in 2 dimensions by Michael Douglas 15 plus years ago. In that case, you need to add a condition that the twist gap is non-zero to avoid things like C equals 1 having a divergent volume. And Cumrun made a conjecture like this for the spring moduli space. And so this jump is really not too far, but it's a different statement that I'm trying to phrase in CFT language. I mean, I might believe this to be true. This is suggested by this hyperbolicity because, right, that cuts off the volume when you're near infinite distance, but you need some other physics to cut off a volume divergence elsewhere, and that's not guaranteed to be there, right? We don't always have S-duality, for example. That's a non-trivial interesting thing. If this is true, then it begs the more interesting question: what other properties does this volume obey? And in particular, yeah.
Sure. With a cutoff or without a cutoff?
What do you mean by cutoff?
Like the circle, that's the interest volume.
Yeah. So I mean, in cases like that, one needs to add a condition on the theory. Yes. I think it should be. So I think this is true. And there's a natural question, which is what sets an upper bound? Right? Is there some piece of CFT data, or perhaps some function of the space-time or conformal manifold dimension, which upper bounds this? That would be fascinating to derive. Certainly, one question this conjecture raises is what must the degeneracy of these higher spin currents be? I'm talking about it as if there's just one tower, but in familiar examples, for n equals 4 super Young Mills, there's a ton of higher spin currents. It's a matrix model, so you have lots and lots of higher spin currents. And you may ask, can you have a vector growth, something like one single tower currents which become conserved at this infinite distance point? I didn't thought too about this, but this seems more exceptional, and I'm not quite sure there are any cases that come to mind. This is more like a vector model, but the vector models we understand don't have moduli. There are some which look like they do largely. This is a large artifact. These are 3D theories without actual conformal manifolds. And so it's be nice to think. This would sort of get at whether this tower must be stringy if you use the Hagedorn growth condition to characterize stringiness. Well, that's the spirit of this question. Okay. So lastly, let me share some unpublished thoughts about the ADS scale separation problem, which I'm viewing as a part of the strong coupling programming of this talk. These are just some modest observations, but I think they will be useful in trying to solve the problem. I won't solve it today, but I hope to help with what I'm about to say. This should appear sometimes. Okay, so let me ask the question in case not everyone is familiar. But simply, are extra dimensions required in the ADS CFT correspondence in the Einstein gravity regime, where the extra dimensions are large? By large, I mean ADS size. For example, if you have a superconformal theory with a continuous R symmetry, must that be geometrized at the ADS scale? Often we assume the answer is yes, but actually there's no proof of that. And this could be a Laplace effect. It's a genuinely stringy problem. I put this in quotes because one doesn't need to ask it in the context strictly of string theory. But if you do, then getting rid of the, say, extra dimensions from a 10-dimensional type 2B point of view requires something like stringy geometry, where you have to pack these dimensions away somewhere and the curvature becomes large, and it does not get answered in the 10D supergravity approximation. This is partly why it's a problem from the bulk point of view. One needs to invoke more ingredients than the familiar ones. And even with maximal supersymmetry, there is no proof of the statement that this R symmetry must be geometrized, say in ADS 5 times S5. In field theory language, there's a question about whether there can be exotic n equals 4 theories in 4 dimensions. That remains an open question. We talked a bit more about this in this white paper I wrote with these authors. You can go there for some further perspective and lots of references on the question. So I'm talking about this here partly because, I mean, for a couple of years now, I'd say there's been a growing appetite for the large NCFT or bootstrap community to really answer this definitively one way or another. And actually, it's moving before. I'm not going to do that today. But I'm going to sharpen the question from a purely CFT point of view. And I hope this helps us solve it. So we will consider sequences of local CFTs, that is, CFTs with stress tensor operators, which have an asymptotic limit of large n and a large single trace higher spin gap. This is just the usual regime of the space of conformal field theories in which we meaningfully can talk about Einstein gravity and geometry in the bulk. It's a parametric limit where higher derivative corrections are suppressed. Now, let's consider the following 3 statements, which are plausibly true. So the first is that every large n large gap CFT of this type must actually have a parametrically infinite tower of symmetric traceless spin 2 single trace operators, where the dimensions of these operators are order 1. This is tantamount to the conjecture of Cumrun friends that scale separation is not possible. The second statement, slightly different, is that if a theory contains a single non-conserved symmetric traceless spin 2 operator, whose dimension is order 1, it must actually have an infinite tower. So order 1, there must be an infinite number of rows. Again, we don't know the answer to this question. And finally, there are no consistent ADS truncations to a finite number of massive spin 2s. This is similar to the second, but when you talk about consistent truncation, this invokes statements about couplings. And so this is a slightly different statement. There have been some works in the literature before trying to construct such truncations. These works here suggested that these truncations might exist. A few months later, that suggestion was ruled out by a computation by Liu and Peng. So back in the day of people looking at sort of novel consistent truncations involving massive vectors and trying to construct Lifshitz and Schrodinger solutions and so on, some work that Hiroshi did as well. This suggestion came under the light, but it was sort of dismissed by calculation. And so the question remains open. Okay. But there are no examples of this happening. Okay. And you notice that I'm talking about spin 2 as opposed to lower spin, and you might be asking yourself why. And that's maybe one of the key points I'm trying to make. So the next point is that spin 2 operators are the smoking gun of large extra dimensions. The type of theory I'm talking about has a supergravity approximation in some number of dimensions, capital D. Okay. This does not have to be little d plus 1, the dimension of the ADS space. That's the question. What can capital D be? But there's a supergravity approximation in some D. And so the spin 2 operators must descend from the d-dimensional graviton. The supergravity doesn't have massive spin 2s, and there are no other fields which have the right quantum numbers to give these types of operators in the lower dimension. So spin 2s are nice from that point of view. Contrast this with scalars, which can be moduli coming from various places, or KK modes, or vectors, which, of course, there exists supergravities where you can couple different numbers of vectors, say representing flavor symmetries in a boundary theory. So spin 2s are unique. Point of view, the intuition for the CFT construction from ADS is the following. If we define N2 as the number of light spin 2s, light meaning order 1 dimensions, then if D, big D equals little d plus 1, then N2 equals 1. That is, you just have the graviton. In other words, if N2 is greater than 1, then big D is greater than little d plus 1. But from the supergravity point of view, you expect this to imply that N2 is actually infinite because of, say, an infinite KK tower on whatever this extra space is. What we're going to do is understand this purely from CFT. What values of N2 are possible? This is the intuition that guides us. Now, this expectation was, let's say, buttressed by some recent works. There was a paper by Cumrun and friends, which, based on some calculation for a certain type of manifold, suggested that the spin 2 spectrum should start at some order 1 dimension. This follows from some diameter bounds of this class of manifolds they consider where the volume is shrinking, but the diameter is not shrinking, which is translated into the statement about spin 2s, because we're talking about the scalar Laplacian. It's a very nice, sort of maybe surprising result they found. There's a paper by Vafa and Intercept, who showed that for positively curved closed Einstein manifolds, which fairly represent the kinds of things we often see in the context of holographic compactifications, at least in supergravity, the gap between any two consecutive scalar eigenvalues is actually bounded by order 1, right? The ratio in particular. So here's a plot, and I'm expected to be able to see the features, but think of this as 4. Okay? With some exception, the right-hand side is exactly 4. Okay. So if the spectrum starts at order 1, then you have an infinite tower of operators whose dimensions are order 1. That's what this suggests from the bulk quantity. So there's some nice works in this context. Now, the second point, now we're really getting to the meat of what I'm trying to say, is that this is a Regge problem in CFT. Most CFT local operators lie on analytic Regge trajectories, which are families of operators interpolated, continued analytically in spin. Here I've drawn part of some trajectories. So the trajectory is, think of it as function J. J is the spin. Nu is related to the conformal dimension. And the physical operators sit at integer spins, where this, say, spin 2 operator here would be stress tensor, be down here at d over 2. And if you go up, then there's going to be some spin 4 operator out here, and so on. This one is the leading trajectory, the collection of operators whose dimensions are lowest for a given spin, analytically continued to a trajectory, a line drawn between them, effectively. And these other ones here are sub-leading trajectories, operators of the second lightest, third lightest, and so on. It follows from these words in CFT that in a non-perturbative CFT, this structure exists. Okay, at least for operators who spin greater than 1, this structure exists. They must all lie on these types of trajectories. Now, in planar CFT, the story changes very simply, but analyticity, with some standard assumptions about the existence of the trajectories themselves, implies that all operators lie on trajectories when the spin of the operator is greater than 1. And so, in particular, the spin 2 operators are on these trajectories. So, at this point, we've transformed the CFT dual of the ADS scale separation question into the following question: how sparse can the single trace spin 2 trajectories be? How many of these are you allowed to have where the dimension of the spin 2 operator is order 1? This is useful because the trajectories are rigid objects, right? They are more tightly constrained than just some collection of numbers which represents the scalar spectrum. So the hope is that this is a useful observation because we're able to sort of bring to bear the full power of the structure of CFT spectra. Okay. Time-wise,
Well, we're almost done with it.
yeah, okay, good. So I should have one more substantive slide on this, then some fantasies, and then we're done. And the final point which really crystallizes this is that this is actually a Regge intercept. Okay, so let me just show the picture. The point is that the existence of the large gap limit constrains the form of these trajectories such that the splittings between any trajectory which has a spin 2 operator on it is order 1 over delta gap squared. So you can look at the intercept, which is where these trajectories cross the y-axis, and ask how dense are these intercepts allowed to be? And that's equivalent to asking how dense the spin 2 spectrum is allowed to be, because the existence of the large gap limit squeezes all these trajectories together. So we've really arrived at the sharpest version of this question, which is what is the smallest allowed number of trajectories with intercept equal to 2? That is the CFT version of the scale separation question that I think will be useful to think more. Okay. So let me make a few comments. We're grading with global symmetry. That's what we should do. Rather, not grading by global symmetry is what we should do because we just want to argue using conformal symmetry. And often there are singlet spin 2s. For example, in the confold compactification. This thinker relatively recently trying to come to bear on this question. I'd say it was suggestive but inconclusive, but it tried to approach it also from a bootstrap point of view. And let me finalize this part of the talk with a conjecture, which is that in fact, finite n2 not equal to 1 should not be allowed. I think it's true that n2 must either be 1 or infinity. Now the big question is n2 equals 1 allowed, aka is scale separation allowed? That's still an open question. But I hope to have lead it to the point where we can try to answer it a bit better. Okay, so time for some final fantasies. Let me state the first. Is it possible that the central charge in 2D CFTs must actually be an algebraic number, or perhaps even rational? Is there really evidence for this? Well, not really in its strongest form, but there's some form of evidence. In 2D CFTs with these n equals 2 symmetry, supersymmetry, and a U1R, there's a C extremization proposal, prescription of these authors. And if that applies, then C is rational. Okay. I'm thinking about this. If C is discretized in the sense of being an algebraic number, then it would be a novel explanation of part of the C theorem. Namely, the part that says a C cannot vary as you vary continuous couplings. Why does it explain that? Well, if C can't move infinitesimally away because it belongs to a discrete set of numbers, then that follows immediately. This would be a nice explanation of that. I think we should take this possibility seriously, given how little we've been able to uncover about alternative CFTs that somehow fall outside of this. And finally, more extreme fantasy is that, in fact, all compact unitary Virasoro or say super Virasoro CFTs would be either rational themselves or exactly marginal deformations of rational CFTs. So if you imagine this picture to actually be true, or some version of it. Let's just take the Virasoro case for simplicity. You have a bunch of middle models, and everything else is some distance away from some rational point with respect to some higher chiral algebra. This would be pretty remarkable. It's consistent with what we know and don't know. Is it really so crazy? I'm not sure. Maybe it is. We all might have our own answer to that question. But, well, this is the fantasy section, so don't blame me. So let me conclude with 60 and thank you for many deep insights, camaraderie, and your stewardship of the fields.
Any questions for Eric?
Very last. So in the 90s, there was some work by Halpern and Correctus, something like that, supposedly constructing two-dimensional CFTs with irrational circle charge and at least at the level of consistent yield. I think nobody ever proved that they were modular at target. Is this a question that maybe is running from modular bootstrap or something?
Yeah.
You are referring to the one, the Virasoro generators are given by bilinear in current with some random coefficients.
Yeah.
Was it, do you happen to remember if it was algebraic? It might be nice to check, but yeah, I think vetting constructions like that is something we should do. I'm not quite sure the modular bootstrap would be the right set of techniques to do that, but
I mean, the point is they had a conception of the so modular.
I mean, checking for a given proposal that it is modular invariant is so the opposite of what the bootstrap can do. I mean, I don't have to tell you this, or maybe you disagree, but
Oh, I mean, there may be that you have to have other states in addition to the currents to make it modular invariant. So we would be closer to your constraints on the non-homomorphic operators in the
yeah. If you see this information that they do determine into a bootstrap approach, then that would be great. Yeah.
Any other questions? One question about the 0,2. You mentioned that it's rational, not a conjecture, based on our maximization of the element of the A maximization. Isn't it true that the spectral flow operator gives you the highest charge operator to be related to C? And that's related also to the for chiral operator, that's proportional to some multiplier. So therefore, if charge is rational, it should be rational because of this would follow. So you don't need that. You don't need more than that, do you?
No, I don't think so. I mean, this is sort of a question. But if it's say it's R instead of U1, this is
That's a question about modular invariance. Doesn't it imply that it should be U1 if it's no gap? If it's discrete spectrum, I think that shows that.
So that's using some extra information, which I think is good to do. But yeah, I wanted to
Modular invariance.
Yeah, indeed. I mean, but also compactness, right? Which one? We're not sure.
If it's not, if it's R, you would get the complete. You wouldn't get a discrete spectrum.
Right.
So you get a complete. So if we're talking about CFTs, which have discrete spectrum, you have no choice. Integral.
That's my feeling as well. So adding that condition might allow you to say something more strict.
Yeah. Any other questions? What's this thing? Shrink again?